In this video, we're going to talk about a function. We're going to give a definition, talk about different ways to represent a function, and then relate that to both a table and a graph and an equation. A function is a relationship showing how one quantity depends on another. So this is a very general relationship that we're describing here, but really it can apply to so many different things. We're really just taking two types of information and showing the relationship between those two types of information. It could be a time or a year and a population. It could be, one example I usually give is a baby's age and a baby's weight. Right? Those two things could be related to each other. A lot of times in math, we label these, right, as X and Y. And so the one quantity here is usually the Y that depends on the X. So there's a lot of names put together for each of these roles, the Y and the X. So I wanted to jot a few of those down for you. The X is usually called the input. And we have a lot of freedom as far as what input we choose to put into our function, or what X values we want to look at. For that reason, the X is called the independent variable. It's independent of anything else. We can choose it, right? We don't have total freedom, but we have quite a lot of freedom, right? We can decide, I want to look at X equals 2, or I want to look at the year 2006, okay? I can choose that. If I put the set of all X's together in one big group, we're going to get to that in just a second, but it's called the domain. Okay, I take that number, that input, I put it into my function. Either I have an equation that I use to calculate, or I have a table or graph, or just a relationship in general. And that's going to be tied with what we usually call an output. Sometimes we label it Y, right? So what we get out, the result that we get, depends on what we put in. So for that reason, the Y is called the dependent variable. The Y that we get depends on the X that we started with. And the set of all Y values together is called the range. So you may see a lot of these words sprinkled throughout this chapter. I always like to write a little bit more specific definition for the domain and range. So the domain is the set of all the X's, but it's a little bit more specific than that. So it's the set of all real number X values. So I take a real number, I put it into this relationship. It's a number that produces a real number Y value. So this would not include X values or numbers that would not compute a Y value. So if I had an X value that I plugged into my equation and it gave me something undefined, that would not be in the domain. I need to only include the X values that produce real number Y values. You could say they were valid inputs, right? Inputs that I could plug into my function or examine my relationship and get an output from it. Then the range is going to be the set of all the possible Y values, right? All the resulting outputs together. Some functions have every possible Y value, any number, any real number. Some functions only have certain types of numbers. Maybe they're only positive, right? And so whatever numbers are possible to get out of my function or my relationship, those are in the range. Okay, the definition I have up here is kind of an informal definition that the book gives. So I added a more formal definition down here at the bottom. So a function could also be defined as a set of ordered pairs, so points x and y pairs, where each x value corresponds to exactly one y value. And this exactly one part is the criteria that we use to make it a function, specifically to kind of distinguish it from any other relationship. So when we say that each x corresponds to exactly one y, another way to put that is 2 points cannot have the same x and different y. Right? So each x value can only give us one output, not two or more. I like to use the idea of a UPC code as a good example for this, right? So when you go to the store and you have an item, each item has a UPC code on the back. And when you take it to the cashier scans that UPC code. So think of that code as the X value. And when the cashier scans the code, she gives you the price, which would be like the Y value, right? So it never happens that you would go to the cashier. For some reason, I'm picturing Target, okay? She would, or he would scan the code. They never offer you two prices. Oh, you could pay $3 or $5 for this item. This item has two prices. Right? That doesn't happen. Okay, that would not be a function. All right. And so for each UPC code, there's only one price, right, in the register somehow programmed in there, right? That would be a function. It could happen though that you pick up two items, different UPC codes, different X values that happen to have the same price, right? So it is possible for a function. It's only a one-sided criteria here that we're talking about. So it's possible to have two different X values that happen to have the same Y, right? And that's okay. So we're going to look at several different ways of describing a function. You can do it verbally. I've just given you a couple examples in words. You could describe a relationship, right? So in words, you could just describe a function numerically, given some data points. Usually this is in a table. Or we could do it symbolically, using a formula or an equation, or we could do it graphically. We could draw a picture, a graph of the function or the relationship. We've seen a lot of graphs lately, and a graph is usually a really easy way to show a lot of interesting phenomenon, right? Relationships. One way to represent a function is with what's called function notation. It's just kind of a condensed way to give us a name for our function, to work with the input x and the output y. So we can say, hey, I'm talking about this specific function f. When I plug in this input x, this is the output that I get. And so it condenses all that information into one small sentence. So because we use this function notation, it is kind of declaring, hey, this is a function versus any other kind of relationship, but also it's going to allow these two things to be interchangeable. So I can use the variable y to represent the output, or I could use f of x to represent the output, which says when I use this input and this function, f of x is the output I'm going to get. So I just have a graph here just to give you an idea about all the connections you could make with that, right? We just graphed in the last video, so you can always go back and look at that. If I were to plug these numbers in, right? If I plugged in -2 squared would be 4. 1/4 times 4 would be 1, plus 3 would be 4. So f of -2, when I use this input into this function, when I plug it in, I get 4, right? And on the graph, that matches up with the point -2 positive 4. So all those things are kind of tied together. We could do the same, we could fill in this whole thing, right? I'll just do a couple more, maybe not all of them. So if I plug in 0, 0 squared is 0, times 1/4 is still 0, plus 3 would be 3. That means that when I plug 0 into the function f, I get 3 out as my y value. And that corresponds to this point, 0, 3. Right? Where my x value is always going to show up in the parentheses, and it's going to be equal to the y value, just like we wrote up here. Okay? I'm not going to fill in the rest because I feel like that maybe is enough to give you an idea of what that's like. Okay, so now I want to give you a chance to decide if something is a function. So we're going to talk about how to do that with a table, with a graph, and then we're going to speak a little bit about the equation part as well. So is this a function? Is a table a function? We're going to go back to the definition. Let me see if I can make that appear up here. There we go. So we said a function is a set of ordered pairs, so I'm going to match up some x's and some y's. And when I do that, it's only a function if each x is paired with exactly one y. We said you could also say 2 points cannot have the same x and different y. Okay, so I'm going to take this away so we can see them both. So which of these is a function? The second one is a function, right? Each x, I have 1, 2, 3, 4, 5 different x's, and each of them have a y value, one y paired with, right? So we would say, yes, this is a function. And if you were asked to justify that, or why, how do you know? You could say something like each x is paired with one y. Okay, what about the first one? Why is it not a function? We have a problem spot, right? The x value of 5 is paired up twice. It's paired up once here with the y value of 2, and it's paired up again with the y value of 0. So we would say no, this one is not a function. If you were asked to justify that, you would say something like the x value 5 is paired with 2 different y's. Okay, so this is how we would identify a function using a table. What if we wanted to decide if a graph was representing a function? Let's look at that. To decide with a graph, same question, right? Is this a function? We use something called the vertical line test. Some people call it the pencil test, right? This is vertical would be up and down, like vertical blinds in your windows. If every vertical line intersects a graph at no more than 1 point, then the graph represents a function. We're really doing the same test. We're just doing it in a very visual way. So a vertical line would represent one x value. So if our vertical line touches a graph in just one spot, that means that x value is just paired with one y value. But if our vertical line passes through more than once, then we have the same x paired with different y, which is not okay. All right, I kind of gave it away, but this one is okay. This is a function, right? Anywhere on this graph, if I drew in a vertical line, I'm just going to draw on one as an example. Maybe, if I can make it straight. Right? It's only going to touch in one spot. So this checks out. This is a function. Each x depicted by the vertical line is only going to touch once and produce one y value. However, over here, there are many places where I could pass a vertical line and it would touch more than once. So this is not a function. Okay, here's, I gave you the equation here, but the grid did not print nicely. But here's an example of a point, right, like 4, 2, and 4, -2. 2 points that would be on this graph, same x, different y. So we're doing the same test, we're just doing it differently. Okay. Now let's talk about an equation. So if I want to, we're not going to ask the question, is this equation representing a function? We could, but we're not going to do that. So what we are going to ask, though, is for you to find the domain for certain types of functions that are written as an equation. So there are two big problem functions, I guess, that have special domains that we're going to start out talking about, right? So the first one is a function that's a fraction. So the denominator of a fraction cannot equal 0 because I can't divide by 0. And so that produces an interesting domain, right? I can't use every number on the number line. There are a few numbers I have to stop using because they are going to create this problem. The second type of function that has a special domain is a square root. So the argument, or the inside of the square root, must be non-negative. So it has to be greater than or equal to 0. Okay, so let me show you what this would look like and give you kind of an example. So we'll start with the square root, right? So here's my function. If you'd rather put a y in place of the f of x, you can do that. That's okay, because they're the same. Okay, for this function to work, I need to be taking the square root of something positive, either 0 or positive. Right, so you could think in your head, what number would make the inside of the square root 0? That's the smallest number I could use. Or that's kind of the dividing line, really, between numbers that work and numbers that don't work. And you could test to see, is it numbers that are bigger than that dividing line or smaller? Okay, you could probably think through it in your head. One way to work it out on paper is to just take the argument. I'm not changing the function, I'm just looking specifically at the argument being the thing inside the square root. I want to make sure that it's positive, greater than or equal to 0. And so I could take this and work it out. So for this example, I'd add 1 to both sides. So what's going to make the argument positive is when I have x values that are greater than or equal to 1. So I can write the domain for this in 2 ways. I can use set builder notation. So it's the set of all numbers x such that, and then I list the criteria. This is my criteria, I just worked it out. Okay, this might be the easiest right now. So you can totally do that. Eventually, we're going to write this in, it's called interval notation. So I'm going to draw a number line picture just to help you see that. Oops. Okay, so any number that's 1, equal to 1, or greater, right? And when I go all the way up to the arrow, that's representing infinity. So again, let me label these. This is set builder notation. And then interval notation, we're going to list the endpoints from left to right. So from 1 to infinity. If I include the endpoint 1, I'm going to use the square bracket. If I didn't include the endpoint, right, if I just started just after 1, I'd use a parentheses. Because the infinity is not an actual number, it's more of an idea of numbers going on forever, we always use the parentheses for infinity. All right, one more. So we also said that the denominator of a fraction cannot be 0. Again, if you don't like the function notation, you can always put in the y. They're the same. So there's one number that's not going to work here, right? That if I plugged it in for x, I would not get a number out for y. And that's the number that's going to make the bottom 0. I could work that out on paper. Notice the setup is different for these two different types of functions, right? For the square root, I want something positive, so I'm using the greater than sign. For the fraction, I don't want it to divide by 0, so I'm using the not equal sign. But I could work it out in a similar way. Five is the problem. Just to kind of make sure you understand why that is, I'm going to plug in 5. Okay, so I plugged in a 5 for x. This is going to give me 3 divided by 0, but I can't calculate this. I can't divide by 0. And for that reason, I don't want to use 5 as an x value. It's a bad one, doesn't work. Okay, so I can use any other number in the domain. In this function, I can't use 5 because it doesn't work. Okay, and we have our same two methods to write the set of numbers in the domain. I want to include the set of all x, any number I want. My criteria is x can't be 5. So again, that's the set builder notation. I don't think I labeled this one. Can I go back and do that? Okay, if you wanted to write this in interval notation, this one gets a little bit interesting. We will talk about interval notation in more depth later on. So I'll just kind of show it to you now in case you want to go ahead and start trying it out. But if you'd rather wait, you can definitely do that. We're going to leave out the number 5, so I use an open circle to show that. Any of the numbers smaller than 5 are fine. Any of the numbers larger than 5 are fine. Okay, so this is actually broken into 2 parts. I'm going to go from negative infinity up to 5. Since the 5 is not included, I'm going to use the round parentheses. Like we said above, the infinity always gets the round parentheses. That's all these numbers smaller than 5. On this side, all the numbers bigger than 5, I'm going from 5 to infinity. Again, I'm not including the 5, so I use a round parentheses. Always a parentheses for infinity. If I have 2 parts like this, I use what's called a union in the middle, and that just says that I'm putting these two groups of numbers into one big set. All right, so hopefully that gave you just kind of a basic idea of what a function is and how we can represent it. It's going to take some time to digest, so I definitely recommend going in and finding some examples to use for practice. Of course, I'll always take your questions. So good luck, and we'll see you next time.